Welcome to the notes for 6.2. For Algebra 2 Honors, we're going to be looking at graphing rational functions when they're in a general form. So the general form for a rational function doesn't look like the graphing form. So when we have a general form for a rational function, we tend to have two polynomials divided by each other. Okay, notice the functional notation here. Now, it could sometimes just be a constant over a polynomial function as well. That could happen. It's not quite the same as graphing form because our denominator may not just be a binomial. It may not just be degree 1. So we might see some different things here. So a vertical asymptote, as a reminder, is that vertical line that the graph approaches but never touches or crosses. Now, this is going to come from the undefined values on the denominator. Just like when we had the graphing form, we could see the vertical asymptotes from the value of h on the denominator, the roots of the denominator. You might have more than one when things are in general form. These roots cannot be factors of the numerator as well. To find the vertical asymptotes, you're going to factor the denominator. And again, it is super important that as you look at these, sorry, I'm just going to try to modify my screen here. There we go. That you are recognizing that the factors cannot be factors of the numerator. If they're factors of both the numerator and the denominator, they are not vertical asymptotes. You'll draw your vertical asymptotes as a dotted line, just like we did in the past. Your horizontal asymptotes are a little harder to find in general form. Remember, horizontal asymptotes, a horizontal line that the graph approaches. It can touch or cross, but it just doesn't happen very often, okay? It is rare, but sometimes when we're close to a vertical asymptote, we might see our horizontal asymptote might actually be crossed a bit by our function. It's not super common. It's not something I want to stress you out about. I just didn't want to tell you something that wasn't not true. To find a horizontal asymptote, we're going to compare the degree of the numerator and the degree of the denominator. And we want to, basically what we're trying to do is see which one's growing faster as we approach very large values. And that's going to help us decide what's happening on the ends, which is, remember we saw that before our end behavior was our horizontal asymptotes. Well, the first type of situation, there are three, is that if the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. This would be something like this. Y is equal to 5x to the third minus 10 over x plus 2. Remember, degree is the highest power. So our degree of the numerator is 3, our degree of the denominator is 1. If we put in very large values, what's happening here is we get very large values on the numerator and smaller numbers on the denominator. And these just keep growing and growing without bound. Remember, our horizontal asymptotes need to kind of turn, all right, to approach that straight line. They need to turn. And what happens here is that these grow without bound if it's bigger on the numerator. Now, they might grow to negative infinity without bound as well. This one looks like it's growing to positive infinity because we've got these large positive numbers. But if the numerator has a higher degree than the denominator, then you will not have a horizontal asymptote. We will not see that turning behavior. However, if the degree of the denominator is larger, then the horizontal asymptote will be y equals 0. That'd be like, let's just take our last example, but switch the numerator and the denominator. This one, we have a cube on the denominator and only a power of 1 on the numerator. So if we put in very large numbers like 5 billion, 700 trillion, what we'd end up with is something very small compared to something that is much larger. And as we start putting in bigger and bigger values, this would end up being the larger grows so much faster than that smaller numerator that we eventually get numbers like 1 over, or maybe it's like 100 or 10 or something over like 1 billion, blah, 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 blah. And what happens is we get these values that get very close to 0, and we get this turning action, and we get this horizontal asymptote at a height of 0. If the degree of the numerator is the same as the degree of the denominator, then essentially what happens is they're kind of growing at basically the same rate. I'm saying basically. This might be something like this. Y is equal to 3 minus 4x squared over 5x squared plus 1. Both of these are degree 2. They are growing at essentially the same rate. Now, you might go, wait a minute, what about some of these other numbers? Well, what happens is we start putting in numbers that are like 5 billion, 8 trillion. The fact that we've got this 3 or this plus 1, they become very insignificant. Now, the -4 and the 5 do still become significant. And so what ends up happening is if you have the same degree on the top and the bottom, you would make your horizontal asymptote will be equal to the line y equals, because it's horizontal, the ratio of the leading coefficients. Wherever those highest powers are, what are those coefficients? On the numerator, it's -4. On the denominator, it's 5. And so this would turn and approach the horizontal line y equals -4/5. So you will definitely want to memorize those 3 situations. And by the way, you'll need them next year and the year after. They don't really go away. So those are important things that you want to make sure. Those horizontal asymptotes are crucial. All right, so for each of these functions, we just want to find the equations of any horizontal and vertical asymptotes. We're not graphing these yet. We just want to find the equations. Now, number 1, we could consider number 1 to be in graphing form if we wanted to, right? Do you see the horizontal asymptotes at +0? However, I'm going to try to shift us towards using our general form and trying to see what we think if we can figure it out from there. Your vertical asymptotes will be from the roots of the denominator as long as that factor is not repeated on the numerator. And it's not. So the vertical asymptote will be x over 2. Now, if I look at the horizontal asymptotes and I look at it through the lens of comparing the degrees of the numerator and the denominator, on the numerator I have degree 0 because I don't have any x's. On the denominator I have degree 1. Therefore, the degree of the denominator is larger, and so I would have the horizontal asymptote y equals 0. Basically, what's happening is that my numerator is not growing as fast as my denominator. So when I put in very large numbers, I get something small over something large, and eventually I get close to 0. Let's try number 2. The denominator will give me the vertical asymptote as long as that same factor is not repeated on the numerator. Please note it's x equals, because it's a vertical line, and it's the root of that factor. So notice the sign change. Now my horizontal asymptote, these ones both have the same degree of power of 1. So now I'm looking at case 3. My horizontal asymptote, horizontal, would be y equals, and I want to use the leading coefficients, and I make a fraction over them. 1 over 1 reduces to 1. Number 3, my vertical asymptote will be the root from the denominator, which is x equals 0. I do want to verify that that's not a factor on the numerator, but it's not. The horizontal asymptote, I will compare the numerator and the denominator, but this time the numerator is larger. So there is no horizontal asymptote here. I'll just write none. What's happening is that this is growing and growing and growing faster on the numerator than the denominator. So I just keep getting numbers, outputs that are larger and larger, and I don't ever get that turning action. Number 4. Now, on 1, 2, and 3, everything was fully factored. Numbers 4, 5, and 6, these are not factored. And you really do need to factor them first before you try to identify your horizontal and vertical asymptotes. So that's what I'm going to do. Now, my numerator cannot be factored here for this one, so I'll just leave it the same. My denominator can be factored, x plus 3 and x minus 3. I do want to verify that those factors are not repeated on the numerator. If they are, that means something different. We're going to learn about that next class. But this one has 2 factors on the denominator. Each one of them will be a vertical asymptote. So this one has 2 vertical asymptotes. One at the line x equals -3 and one at the vertical line x equals +3. For my horizontal asymptote, I have the larger degree on the denominator. So this is case 2, which tells me that the horizontal asymptote is at y equals 0. That's because I'm growing faster on the denominator. So I have something small divided by something big. And when we do that, we start approaching numbers that get close to 0. Number 5. Again, I need to start by making sure everything is factored. This one, the numerator, can be factored with a GCF. The denominator is already factored. The denominator will give me the vertical asymptotes. This one only has one factor, so it's only one vertical asymptote. Again, notice the x equals. This is a line. You must have x equals. If you just write -1, you will not get it correct. The horizontal asymptote actually is easier to find in this case before I factored it. The reason I factored it was to verify that my factor on the denominator was not repeated on the numerator, because if that happens, we have a different unusual situation. The horizontal asymptote, remember I'm comparing the highest power. When the highest power is on the numerator, there is not a horizontal asymptote. Number 6. Again, I'd like to factor. Now that numerator, I'm looking at that and I'm like, what? There is no GCF on the numerator. I don't actually know how to factor that. In fact, it doesn't factor. I'm just going to leave it. On the denominator, there is a GCF. I'm actually going to do some factoring work to the side because I can tell that this one's going to require more than one step. After I factor out that GCF of x, this remaining trinomial can be factored as x plus 4 times x plus 1. Now I want to verify that none of these factors on the denominator are repeated on the numerator. If they are, I don't get to count them as vertical asymptotes. There's something else. They're called holes in the graph. We'll talk about those next class. But what I'm going to do now is identify my vertical asymptotes. Every factor on the denominator, as long as that factor is not repeated on the numerator, is a vertical asymptote. So this would give me x equals 0. Notice I'm using the root or the solution here. And I must write this as x equals, these are lines, x equals -4 and x equals -1. Now for my horizontal asymptote, I'm going to compare the degree of the numerator and the denominator. X to the third is the highest power in the numerator. X to the third is the highest power on the denominator. Since these have the same power, this is case 3. They have the same degree. So the line would be written, the horizontal asymptote is y equals p over q, where p and q are the leading coefficients. So I'm going to make a ratio. So horizontal would be y equals 7 over 1, which divides out to just 7. Our challenge now is to take this same concept, and now that we know how to find the horizontal and vertical asymptotes, to actually make the graph. Here are your steps. Make sure everything's factored. Use the zeros of the denominator to identify any of the vertical asymptotes, as long as that factor is not repeated on the numerator. Compare the degree of the numerator and denominator to identify any horizontal asymptotes. I should say any. Sorry, I'll fix this on your copy before we make copies. We'll compare the degree of the numerator and denominator to find our horizontal asymptotes, if there are any. We'll start by sketching those. And then what we're going to do is we're going to test a point on either side of any vertical asymptotes. We want to create an ordered pair, and we'll use that to fit the curve to the asymptotes. And this will make more sense when we actually do the problem. Now I'm going to do number 1 in 2 ways. Okay, I'm first going to do number 1 the way we did it last class, and then I'll show you how we would do number 1. Well, actually, I guess they're kind of similar. All right, our vertical asymptotes from the denominator, which would be x equals 2. Our horizontal asymptote, since the degree is larger on the denominator, is y equals 0. Now, this one's also in graphing form because I have a binomial of degree 1. On the denominator, you may have remembered the HK. You can still see that here. You can only do that if this is a binomial degree 1. Okay, if we start having other degrees, this doesn't work anymore. So my horizontal asymptote is right here. And now what I'm going to do is I'm going to test a point on either side of my vertical asymptote. My vertical asymptote is at 2. I like to move one to the right of that and one to the left of that. And I'll plug that in. I have negative 3 over 3 minus 2 is 1. So this is the point 3, negative 3. And if I fit that to the curve, now hopefully that makes sense. We saw already that this negative should flip our graph over. Okay, so this is a vertical reflection. If I plug the 1 in, I have negative 3 over 1 minus 2, which is negative 1. My output is positive 3, so the ordered pair 1, 3. Now, this one really, we could have graphed with what we knew from last lesson. That's not going to be true as we continue moving on. Let's take a look at number 2. First of all, I want to make sure everything is factored, and this denominator is not factored, so I'm going to start there. This would be x plus 1 times itself. You could write that as x plus 1 times x plus 1. I'm going to write this as x plus 1 quantity squared because there's something I want you to see about this. Now, when that factor repeats on the denominator, it's still a vertical asymptote. It's just there's only one of them. There's not two. This is a vertical asymptote at x equals negative 1. Again, if I compare the degree, I have a higher degree on the denominator. So the horizontal asymptote is at y equals 0. And now I'm going to just test a couple points on either side of the vertical asymptote. To the right, I'll test 0. To the left, I'll test negative 2. And I'm just going to plug that in. I'd have 5 over. Now, I find it easier to plug it into this. Personally, you don't have to, but I find it easier. If I plug into 0, 0 plus 1 is 1. 1 squared is still 1. And I get the ordered pair 0, 5. That's also my y-intercept, notice. That's because my input for x is 0. If I plug in a negative 2, I have 5 over. Again, I like the factored form. Negative 2 plus 1 is negative 1. Squared is 1. Notice I'm still getting an output of 5. Oh, let me fit this to the curve. This looks something like this. And this looks something like this. Now, that's unusual. We've not seen that before. Every other one of these rational functions that we've graphed so far, we've had like one on the top and one on the bottom, and we could switch that. You might wonder, why does this one look different? Let's think about the signs of our output. On the numerator, we have a positive. On the denominator, because I'm squaring things, I have a positive. I can only have positive outputs. I can only be above the x-axis. That's why these look like this. Okay? I could only be positive because I have only a positive on the numerator and only a positive on the denominator, and that's why it ended up looking like this. Now I'm realizing that I did not do the domain and range for these, so I'm going to do that really quickly. Number 1, the domain, remember, is all values of x, but not the x where there's a vertical asymptote. And the range is all values of y, but not the y value where there's a horizontal asymptote. Same type of thing for number 2. Domain would be all values of x except not at the negative 1 where there's the vertical asymptote.